Unit 1, Lesson 3. Objective for today is limits involving infinity, which means we're talking about vertical and horizontal asymptotes. First, let's talk about vertical asymptotes. We're going to take a look at this graph here as I'm reading the definition. If f of x approaches positive or negative infinity as x approaches c from the right, this one's going to negative infinity, or as x approaches c from the left, this one's going to positive infinity, then x equals c is a vertical asymptote. When you're looking at a graph, a vertical asymptote is easy to identify, but algebraically, if you're looking for a vertical asymptote, it's going to be where the denominator is equal to 0 and can't be reduced. So let's look at an example where you're asked to identify the vertical asymptote. Number 1, f of x equals x over x squared minus 1. So we have a denominator here. The first thing we'd want to do is see if we could reduce this denominator, or this rational expression. So this is difference of perfect squares. I could factor the denominator, x minus 1, x plus 1. Now, since nothing cancels, I would want to set the denominator equal to 0. T time. And I have two vertical asymptotes. X equals positive 1 makes the denominator 0, and x equals negative 1 makes the denominator 0. And since it can't be reduced, it would be a vertical asymptote. Let's try another one, number 2. F of x equals x squared minus 4x minus 5 over x squared minus x minus 2. Again, we should factor. So I was able to factor both the numerator and the denominator. Now, you might be thinking, why is she worried about the numerator when we're worried about when the denominator is equal to 0? Well, you always have to worry about if something can be reduced. Look what happened when I factored this. There is a common factor of x plus 1 that could be reduced. That means that x being negative 1, that would make the denominator 0 there, is actually a removable discontinuity. It cancels out. It is then not a vertical asymptote. It's actually a hole in the graph. But we were not able to get rid of this x minus 2, in the denominator. So where x minus 2 equals 0, meaning x equals 0, that is a vertical asymptote. Last thing to remember is that you could never cross over a vertical asymptote on a graph. These values keep getting closer and closer and closer to the vertical asymptote, but can never cross over. Let's consider the function f of x equals 1 over x. This is one of our functions that we really need to know how to sketch and understand its properties without the use of our calculator. Since we're talking about vertical asymptotes, let's take a look at the vertical asymptote for 1 over x. First of all, we know the denominator can't be 0, and as we approach x equals 0 from the right and the left, our function is going to positive and negative infinity. Now, something has to be said about answering a limit with infinity. So we said that the limit as x approaches 0 from the right, that's coming in on the road from the right side, of 1 over x is equal to positive infinity. Now, infinity isn't a real number, so you could actually report this answer as does not exist, which would be true. The thing about saying infinity is it's more descriptive, that if I wasn't looking at the graph, then I would understand that the values were getting larger and larger and exactly what was happening. Same thing here. From the left, it's going to negative infinity. I now have this picture that we have this hyperbola that's splitting, one positive infinity, one negative infinity. However, as a solution, if you said, oh, that doesn't exist, that's true also. Infinity is not a real number, so the limit doesn't exist. Let's take a look at this one. Evaluate the following limit. The limit as x approaches 2 from the right of x minus 3 over x minus 2. Anytime you see from the left, from the right, you always want to take a second and see if you've fully answered the question. Now, an easy way to do this one is if this is a free response question, the way that I wrote it out here, if we look at x equals 2 makes my denominator 0. There's no way of simplifying this, so that means x equals 2 must be a vertical asymptote, and you could answer this question with that this does not exist, because we know that x equals 2 is a vertical asymptote. But that's way too easy for BC Calculus. This is not going to be a free response question. This is going to be a multiple choice question. on the part where you're not allowed to use the calculator, and you're going to have to decide between positive infinity or negative infinity. Now, you know it's one of those because you know it's a vertical asymptote, but how do you decide which way it's going? If we were allowed to plug it into the calculator, so easy, you take a look at it. But since we can't plug it into the calculator, we need to make our own graph or our own table of values in order to see what's going on. Are these values getting bigger or smaller as we approach 2 from the right? You don't really need both a graph and a table, but I'm going to do both just to make sure I kind of get everyone on board with me. As x approaches 2 from the right, that means I'm coming in from the right side, the values that are larger than 2, and getting closer to 2 from the right. So these are going to be the values that I start with when I make my table of values. I'm going to start with the whole number of 3 and see what happens. What's my y value? So if I plug 3 into my function, I get 0. So we're at 3 comma 0. Well, I need to get a little bit closer. Now, I didn't start all the way out at 5 because remember, for a limit, you want to get closer and closer and closer, arbitrarily close to the value. So let's move in one more, that if we're going to be approaching from the right, let's see what's going on at 2.5. So plugging in 2.5, I get negative 0.5 on the top and positive 0.5 on the bottom. Well, anything divided by itself is 1, so this is going to be negative 1. So at 2.5, I'm down here at negative 1. So connecting the dots, I might already know the answer, that this is approaching negative infinity. Let's do one more just to make sure we have a full pattern. Let's try 2.25. Let's get a little bit closer from the right. So in the numerator, I've got negative 0.75 divided by 0.25. Now, if these were in decimals, 75 divided by 25 is 3. So 0.75 divided by 0.25 is also 3, but it was negative, so negative 3, which makes my thought about that I'm going to negative infinity confirmed. That I know it's a vertical asymptote because x equals 2 would make the denominator 0. And now that I see as I come in from the right by making a table of values, graphing it just really solidified the visual that this answer would be negative infinity. All right, enough about vertical. What about horizontal asymptotes? Well, by definition, if the limit as x goes to positive or negative infinity of a function, if that equals a real value, I'm calling it b, then y equals b is a horizontal asymptote. Notice it's y equals because it's a horizontal line. The big difference here is that x is going to positive or negative infinity this time, not the solution, but the x value. So let's go back to our example 1 over x. What happens as x goes to positive infinity? I went back to my graph here. X going to positive infinity, that's left and right. That's my horizontal asymptote. So now I'm traveling this way. As x goes to infinity, this is approaching 0. That means my limit is 0. The limit is 0, which then I can report that means y equals 0 is a horizontal asymptote. Let's take a look at another example. Now, when we see something like this, the real algebraic way to go through this is to find the largest exponent. So in this case, x cubed is the largest exponent in both the top and the bottom. So x cubed is our largest exponent, and divide through all the terms by that largest exponent. So I took the given problem, and each of the terms I divided by x cubed. And now I'm going to reduce. So x cubed goes into x cubed, that would reduce to 1. Here I would be just left with an x on the bottom. These x cubes reduce, and this I would be able to reduce the exponent in the bottom to squared. Now the properties of limits allow us to take the limit and look at each term. Let me rewrite it first. Now that I've rewritten it nicely, I can look and go, all right, the limit as x goes to infinity of 1, well, that's 1. This term, the limit as x goes to infinity, well, when x is in the denominator, well, we looked at that over here. As the denominator of a fraction gets bigger and bigger and bigger, it goes to 0. So any term that still has x left in the denominator is going to go to 0. So on the top, I've got 1 minus 0 plus 0. And then on the bottom, 2 minus, since this has x squared left in the denominator is going to get bigger faster, and so it's going to go to 0. So this is 1/2. Now, some of you are thinking, why is she doing all this algebra? I could just look at this and say 1/2. Since you've already seen this before, you know that there's a trick for this. And yes, that's how I am going to want you to do this, by the trick. But it's good to see why this trick works and the real way of doing this, because conceptually, this idea of dividing through by the largest exponent is a skill that will come back to you, that it's good for you to know why this trick works. But if we go to the idea of the trick says find the largest exponent in the numerator and the denominator, like I started off saying, but instead of doing all this algebra, you can ignore the rest of this problem. It doesn't genuinely cancel out, but theoretically, as x goes to infinity, the largest exponents are going to dictate the behavior of the function. And then you compare them. Since they're the same, you pull their coefficients, and we'd be able to say 1/2 without doing all of this extra work. So what is this trick? Let's take a look at it. The trick is compare the function in the numerator and the denominator, which is growing at a faster rate. If they're growing at the same rate, you pull their coefficients. If it's bigger on the bottom, then 0 is the answer. As the denominator of a fraction gets bigger, the y value gets smaller. It goes to 0, and y equals 0 then is a horizontal asymptote. Bigger on the top doesn't exist. That means it's heading to positive or negative infinity. This doesn't only pertain to rational expressions that have polynomials in the numerator and the denominator. It can be really any mix of functions, and if you're looking at the limit as x goes to infinity, this trick applies. So I took a second and made a list of the slowest growing functions to the fastest growing functions. So starting off with the first one, constants are the slowest growing functions because they're constant, they're not actually growing, but it is a function still. Then we've got ln x. The natural log function continues to increase to infinity, but painfully slow. Then we've got our polynomial functions where x is the base and you have some numerical exponent. And if you're comparing polynomials to each other, like we did in that example, you're looking at the exponent and comparing if that's bigger or smaller. But growing faster than any polynomial is an exponential function. Exponential means that the number is in the base and then x is the exponent. So things like e to the x, 2 to the x. As long as the value is greater than 0, then we're going to be growing faster than our polynomial functions. Then next, this you haven't seen for a while. This is the factorial, not just an excited x. X factorial grows faster than any exponential functions. Factorials, you learned back when you were learning the counting principle. Factorials, you take that number 5, for example 5 factorial, then times 1 less, times 1 less, times 1 less, until you hit 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. X factorial has the same idea, that it would be x times x minus 1, x minus 2, and since we don't know what x is, we would have to do a dot, dot, dot until we hit our 2 times 1. All right, and then the fastest growing function is x to the x, where x is in the base and x is in the exponent. Now, it's not always going to be just those two terms, x to the x. For example, here's a function f of x, e to the x ln x. That's really equivalent to x to the x. How's that? Well, let's break it down a little bit, because all of these properties where you're going to be able to manipulate expressions, you've already learned, but you have to make sure that you're thinking with that mindset. Let's take a look at e to the x ln x. First thing that we're going to need to remember are properties of log or natural log, and there are 3 of them. First one is that exponents can come down to the front. So the ln of a to the b power is equivalent to b to the a, and vice versa. It goes in both directions. Second, Multiplication splits to addition. So if we're taking the natural log of two things being multiplied, we can split that to ln of A plus ln of B. And last, division splits to subtraction. So the ln of A divided by B is equal to ln of A minus the ln of B. So using these properties, I can rearrange our expression by moving the x up as an exponent. And then e and ln are inverses of each other. So e to the ln would cancel out, and this is why this expression is equivalent to x to the x. So let's look at an example. The limit as x goes to infinity of ln x over x to the fourth. The x goes to infinity lets you know that you're thinking about, well, which part of this grows faster, the numerator or the denominator. So ln x is increasing but painfully slow. So x to the fourth is going to grow faster. So if it's faster on the bottom or bigger on the bottom, then the limit goes to 0. If you were asked to identify the horizontal asymptote, you would then write the equation y equals 0 is a horizontal asymptote. Last thing I want to talk about are functions that behave differently, positive to negative infinity, because I've just been saying as x goes to infinity so far, and really the answers would be the same for both positive or negative infinity. But there are some functions, like exponential functions, that behave differently from positive to negative infinity. E to the x is another one of those functions that you should just understand how to sketch it and its basic properties without the use of a calculator. It's an exponential function. It grows like this, passes through the critical point of 0, 1. So if we look at the limit as x goes to infinity of e to the x, as x goes to infinity, that's further and further and further to the right. Well, this thing is headed up to positive infinity, or we could say it just does not exist. However, if we switch our value to negative infinity, as x approaches negative infinity, it is approaching a horizontal asymptote. The limit is equal to 0, so then we would be able to say y equals 0 is a horizontal asymptote. Now, in number 7, I should have mentioned that if the limit doesn't exist or goes to infinity, then there is no horizontal asymptote. All right, let's look at another example. 9 and 10 are actually the same function, but in number 9, I've got the limit as x goes to positive infinity of e to the x plus 3 over 4 e to the x minus 2, and the limit as x goes to negative infinity of e to the x plus 3 over 4 e to the x plus 2. So, we've been talking about indeterminate forms. And really, the only one we've talked about is 0 over 0 means that you have to kind of do something else. But another indeterminate form is when you get infinity over infinity. So if we look at number 9, e to the x as x goes to infinity is infinity. Plus 3, but infinity. And also the denominator is infinity. So infinity over infinity is an indeterminate form, meaning this limit still might exist, and what we have to look at is comparing the numerator and the denominator and which one's growing faster. So e to the x is the term, or the fastest growing term in the numerator and the denominator, and since they're the same, we would go to our trick and pull their coefficients. But as x goes to negative infinity in number 10, well, when we're thinking about e to the x going to negative infinity, that goes to 0. So this actually has nothing to do with our trick. We're basically just evaluating by seeing what happens as we go to infinity. So this is going to go to 3 over negative 2, or negative 1.5. Another function that can kind of mess you up when we're talking about positive and negative infinity is absolute value. That's because absolute value is secretly a piecewise function. It's equal to negative x if x is less than 0, and positive x if x is greater than or equal to 0. So for 11 and 12, again, I gave us the same function, but 11 is going to positive infinity, and 12 is going to negative infinity. So when I take a look at this and compare the fastest growing term in the numerator and the denominator. They're really both an x. So the trick says pull their coefficients. Well, in the numerator it's 2, but in the bottom it's this absolute value. So I have to think about, well, which way are we going? We're going to the right as x goes to positive infinity. So as x goes to positive infinity, this is going to behave as the positive value of x. So for this one, this is going to be 2 over 1 or just 2. But when I take the same problem and switch to going to negative infinity, I would still decide that they have the same exponent, that they're growing at the same rate. The numerator stays at 2, but as I go to negative infinity, then that value is going to be the negative value of x. So this actually changes and is going to be approaching negative 2 as we go to negative infinity. So exponential functions, absolute value, you really have to pay attention to if you're going to positive or negative infinity. All right, last one. The limit as x goes to negative infinity of cosine of x to the 5th plus 1 over x to the 6th plus x to the 5th plus 100. Well, this looks really complicated, but it's really not as bad as it looks. First of all, I'm noticing that it goes to negative infinity. But sine, cosine, they are symmetrical, positive infinity, negative infinity. So I'm just going to think about, all right, what part of this is growing faster? Now, the cosine part of this on the outside is not really where I'm focusing in the beginning. Look at where my x's are. They're in this rational expression here, where if I look at the largest exponent in the numerator and the denominator, I'm comparing x to the 5th over x to the 6th. So as x goes to infinity, if it's growing faster in the denominator, it's going to 0. However, ours is not just going to 0. We still have that cosine there. So inside the parentheses is what's going to 0. And now I would have to take the cosine of 0. So my final answer is 1. Great work. I know this is tricky, but I need to get through a lot of different examples so that you're not hung up by any of the ones they throw at you.